concept, or the other term still in the nuclear physics, is relative atomic mass. Relative atomic mass. Relative atomic mass, which is represented by RAM. Relative atomic mass. Now, how are you going to describe relative atomic mass? By description, the relative atomic mass is the average of the masses of isotopes present in naturally occurring specimen of an atom. In short, you just say the relative atomic mass is the average of the masses of an isotope. That means you are going to add all the masses present in a particular isotope. You divide that by the number of isotopes present in that atom. Now, if there are 4 isotopes, take the masses of all the 4 isotopes, divide that by 4. That becomes the relative atomic mass. For instance, we discussed 2 isotopes of chlorine. We said the first one is 3517, and the other one is chlorine 3717. That was the other thing we did. So as a result of this one, the isotopic relationship for chlorine, again, it is clearly, vividly decided or accepted that chlorine belongs to 3:1 in terms of ratio. That the isotopic form of the chlorine takes the pattern of 3:1. What is the meaning of that particular ratio? What I said a few minutes ago is that chlorine takes the form of mathematical relationship in ratio of 3:1. What is the meaning of 3:1? Since we have got 2 isotopes of chlorine, the 3:1 tells you that there are 3 atoms that are chlorine 35. There are 3 atoms that are chlorine 35 and 1 atom that is chlorine 37. Have in mind, we said there are 2 isotopes. And if there are 2 isotopes of chlorine, the ratio for the chlorine isotopes now becomes 3:1. Tells you that for every chlorine molecule, there are 3 of chlorine 35. Chlorine 35 occurs 3 times in that, and chlorine 37 occurs 1. So that becomes 3:1. If that takes us now to the analysis here in the calculation, we are going to find the average. Average means we add all the masses divided by the number of values we have added. Now for this column, we said chlorine 35, there are 3 of them. So for chlorine 35, there are 3 of them. When you want to bring that here, it becomes chlorine 35 plus chlorine 35 plus chlorine 35. There are 3 of them. When you bring that to this column, we say there is a particular value of chlorine 37, just one value for chlorine 37. So that comes here as plus 37 because there is one value for that. You divide that by how many values have we added here? 1, 2, 3, 4. Average mean we are going to divide that by 4. So what I will do now is to say 35 plus 35 plus 35 plus 37. When I do all of this calculation, I am going to get a figure of 142. I will have 142 divided by 4. And when I divide 142 divided by 4, I will get a value that is 35.5. That value that is 35.5 is one of the things that is very unique even in the chemistry. And that becomes the relative atomic mass for chlorine. So for the relative atomic mass of chlorine, it occurs in the ratio of 3:1. The 3:1 tells you that to every chlorine atom, there are 3 atoms that are chlorine 35 and 1 atom that is chlorine 37. It takes us to another term. And the other term we want to make use of is relative mass units. Relative mass units, or atomic mass unit in short. We call that atomic mass unit in short, atomic mass units. Atomic mass unit is represented by AMU, atomic mass unit, AMU. Now in the description for the atomic mass unit, the atomic mass unit is a standard that is used to compare the mass of an isotope with carbon-12. Anytime you compare the mass of an isotope with the value of carbon-12, any relationship or whatever you get is known as the atomic mass unit. So it's like we are going to take the mass of a particular isotope, we compare that with carbon-12. Anytime a particular value is combined with carbon-12, that is what we call atomic mass unit. It becomes the atomic mass unit. From the atomic mass unit, it takes us to another term that we want to look at. And that particular term is known as mass defects. We call that mass defects. Mass defects. Few minutes ago, when I was describing the nucleus of the atom, I said the nucleus contains the proton and the neutron. So the particles that are present in the nucleus are the proton and the neutron. Now there will be a difference in mass between the nucleus and the particles themselves. What do I mean by that? Let us say this happens to be the nucleus. Inside this nucleus, we have proton, we have neutron. Now these two particles, you are going to put their two masses together. You take the mass of the proton, you take the mass of the neutron. Whatever you get will be the particles that are present, the mass of the particles that are present in the nucleus. Now the nucleus itself has got its own mass. There is a mass for the nucleus. So the nucleus also has nucleus mass or mass of the nucleus. Nucleus mass or the mass of the nucleus. And this particular one becomes the mass of the particles. Mass of particles that are present in the nucleus. Now there will be a variation between the mass of the nucleus and the particles that are present in it. When you compare the mass of the nucleus and the two particles put together, the mass of the nucleus is always less than the mass of the two particles. By that, the mass of the nucleus is always less than the mass of the two particles. The two particles now are the proton and the neutron. When you put the mass of the proton and the mass of the neutron together, whatever you get will be greater than the mass of the nucleus that is contained in them. The difference between the mass of the nucleus and the mass of the two particles that are present in the nucleus is known as mass defect. That means the difference that will exist between the mass of the nucleus and the mass of the two particles put together is known as mass defect. So if that is the case, let us say the nucleus is 10 grams, and the two particles, when you put together, you call that, you get a value 15 grams. The moment you say 15 grams minus 10 grams, any answer you get here, 15 minus 10 is given us 5 grams. This one we have got is the mass defect, which is the difference between the mass of the particles present in the nucleus and the nucleus itself. And always, the mass of the nucleus is always less than the mass of the two particles put together. Now, if that is the case, we have a particular scientist known as Einstein. Einstein now brought up an equation that is used to link the mass defect already, which we said is the difference between the mass of the nucleus and the particles that are present with the mass itself and the speed of which the electrons will be moving. So if that is the case, Einstein was able to bring an equation that capital E equals n, we have delta n c squared. We have the expression now to bring here that capital E equals delta n c squared. Most of the time you just say E equals mc squared. Now what does E represent? What is M representing and what is C representing? The E here represents the energy. E is representing the energy, and the N you see in this equation becomes mass defect, which is the difference between the mass of the nucleus and the particles present. That becomes mass defect. And the C represents the speed, the velocity or the speed. The velocity or the speed. If this velocity or the speed is in vacuum, the constant for that becomes 3 times 10 to the power 8 meters per second. So the speed of the light in vacuum, when the light is traveling in an empty space, vacuum, it means the space is empty. Anytime the particle travels in vacuum, the velocity or the speed of that particle becomes 3 times 10 to the power 8. So if on the question or wherever somebody says the particle is traveling in vacuum, the speed becomes 3 times 10 to the power 8 meters per second. It's a constant. Most of the time they don't give that.